Hello, I'm Mladen Čičić from KTH Royal Institute of Technology, and I'll talk about the front tracking transition system model and what you can use it for. I like starting my talks with an ugly picture such as this. We all know that traffic congestion is a problem and it's only likely going to get worse in the future. And in recent time, the control community has been getting more and more interested in tackling this problem, in part due to the introduction of new technology in the framework of the intelligent transportation system, as well as autonomous vehicles and so on. So when talking about traffic control in general, one problem that we are often interested in tackling is bottleneck decongestion. So if you have a road of 3 lanes going into a road of 2 lanes, dropping 1 lane, then this lane drop constitutes a bottleneck, and unless the traffic is very light, we are very likely to see some congestion building up at this bottleneck. So one thing that makes the situation even worse is a phenomenon known as capacity drop. So once this bottleneck gets congested, its capacity will be reduced compared to if it were in free flow. And furthermore, it is known that this transition between free flow and congestion happens stochastically. So for the same level of demand, we might have a bottleneck being in free flow or being in congestion, either way. One way we can try to deal with this is by organizing vehicles into so-called controlled moving bottlenecks and then using them to regulate the inflow to this bottleneck. Either way, if we want to do any kind of control design, we first need a model that is complex enough to capture all of these relevant phenomena, but also simple enough so as to be conducive for control design. And our proposal for this role is the front tracking transition system model. So first let's talk about some classic traffic models. Probably the most classic one of them all is the Lytle-Witham-Richards, or LWR model. This is a first-order PDE, or a conservation law, where the traffic density is the conserved quantity and its evolution is given based on the flux function. So here we choose to use the triangular flux function, and at first, if the traffic density is low, we find ourselves in the free flow regime, and as traffic density increases, so does the traffic flow, until we hit the critical density, after which, if we keep increasing the traffic density, we find ourselves in the congested mode, and the traffic flow will decrease as the density increases. So if we have a situation like this, a road with 4 zones with different traffic densities on them, then the solution to LWR might look something like this. So there will be a number of plots of this nature throughout the talk, so it would be good to get acquainted with them right away. On x-axis we have the space, and on y-axis we have the time. And the traffic density is shown in the plot color-coded. So the brighter the colors, the hotter the colors, the denser the traffic is. And one way we can try to find this solution is by employing one of many numerical methods. Probably the most well-known one is the Godunov scheme, or finite volume discretization, or as it is known in the traffic community, the cell transmission model, or CTM. So what we're doing in this scheme is splitting the road into cells and then tracking what happens with the traffic density inside of each of these cells based on the traffic flow between them. So how would a solution based on CTM look like? Well, since we have 4 distinct regions of different traffic density, we might want to split this road into 4 cells. However, if we do that, it's immediately apparent that the resolution of this solution is very bad, and we need to do something about that. So you can say, well, why don't we just use smaller cells? And we can do that, of course. However, then we have a problem of a very large number of states that we need to track. Furthermore, you can now see another effect has been introduced. You can see that there is some diffusion happening in here. And that is due to the nature of this numerical method. Now, while this diffusion might not be harmful necessarily, at least in some applications, it is definitely not stemming from the underlying PDE model, so we still want to get rid of it. And our solution is to instead use a different numerical method, which is called front tracking. So whereas the cell-based numerical methods try to find an approximate solution to an exact problem, what front tracking does is try to find an exact solution, but to an approximate problem, so a problem that is given in an appropriate form. And the way it does that, so given the LWR with some initial conditions described by function rho 0, what we do is, first, we approximate this flux function as continuous and piecewise linear, and approximate the initial conditions as a piecewise constant function. Then, we solve Riemann problems for initial state discontinuities, so wherever we have a jump in the initial state. And then we track the wavefronts or the discontinuities that originate from these Riemann problem solutions until some of these wavefronts collide, at which point we have a new Riemann problem to solve and back to step 2. One interesting thing to note is that if the flux function is already continuous and piecewise linear, and the initial conditions are already given as piecewise constant, this method actually introduces no approximation. So instead it gives an exact solution to an exact problem. And furthermore, it gives us a rather nice form of this solution because, for example, in this case, at most we're tracking 4 fronts and describing what the traffic density is between them. So that is all well and good, but how do we make a model out of this? So due to the intrinsically hybrid nature of what happens when we're doing front tracking, we need to go with a fairly general class of models. We need to go with a transition system model. So the set of states that we're tracking consists of, first, time. We need to know what time it is. Then the position of these wavefronts and the traffic densities between them. Next, we need to know the number of active states, and we make a choice to allow the flux functions to be a state instead of having one flux function that is valid for all of the road. We can have each of the zones have flux functions of their own, and we are doing that in order to be able to model bottlenecks. Now, the active states are those states that at any given time are needed in order to reconstruct the traffic density wholly. So for example, from time 0 to time t1 we have 4 active wavefronts and 5 different densities, then 3 active wavefronts, then 2. Then the initial state can be any state that is valid, and all of the external inputs, which would be discussed soon, are taken as just inputs. The most complicated part of the model are its transitions. So if we are only interested in solving LWR, all we need are these 3 basic transitions. First, we need the passage of time, which describes how the wavefronts move as you advance time. Then we need the front interaction transitions, and this is basically describing what happens when 2 wavefronts collide. And we need the homogeneous Riemann transition, and this one essentially encapsulates the process of solving Riemann problems and getting the wavefronts that originate from that. Now, if we have different flux functions, then we need the heterogeneous Riemann transition as well. And this one is very similar to the homogeneous counterpart, but since now we're solving a Riemann problem at an interface between 2 flux functions, we need to externally define the velocity of this interface in order to get a unique solution. And then finally, we define some helper transition, which will make it easy for us to implement additional features. So the state insertion transition simply adds 2 wavefronts with some density between them, and the flux function transition changes the flux function of some zone. For example, this whole solution can be described in only 6 transitions. So first we take a homogeneous Riemann transition, which creates this rarefraction wavefront. Then we can advance time by using the passage of time transition until these 2 wavefronts collide, at which point we use front interaction transition. Then we can advance time further, get another front interaction transition, and from this point on we can advance time indefinitely and nothing structurally changes in the model. So we were talking about bottlenecks in the beginning, so let's see how we model them in this framework. First, a bottleneck can either be due to road geometry, like a lane drop, or just due to having a slow vehicle on the road, like this truck. And either way, the way we model it is by having a different flux function be valid in the zone of the moving bottleneck. So whereas the rest of the road will be described by the default flux function, the zone of the moving bottleneck will instead have a reduced version of the flux function valid there. And if we want to add a moving bottleneck, all we need to do is take a state insertion transition followed by a flux function transition. And the results you see here, so outlined in red, you see the trajectory of the moving bottleneck, and there is some congestion building up upstream. Now, if we have a static bottleneck, we might instead want to deal with stochastic traffic breakdown. And if the flow at this static moving bottleneck is too high, then we say that there will be a traffic breakdown after some time theta. And we model this time to breakdown as an exponentially distributed random variable, which is parameterized by the level of flow that we have at the bottleneck. And once this time elapses, we transition from the free flow state into the congested state. And it looks something like this. So after some time theta, the bottleneck is now active and there is some congestion building up upstream of it. Now, if this congestion is dissipated at some point and the flow at the bottleneck drops below the dissipating flow, then we say that this bottleneck returns to free flow. Another interesting thing to note is that while the bottleneck is in free flow, we keep regenerating the theta again whenever the traffic density at the bottleneck changes. And since this theta is exponentially distributed, we can do this as often as we want, and it does not really change the overall behavior of the system. So now that we have this model ready, we can use it for bottleneck decongestion control. And the situation that we're looking at is as you see here. So we have a 3-lane road and a lane drop bottleneck towards the end of it. So if we don't do anything, eventually higher density traffic will reach the bottleneck and we will have a traffic breakdown. Instead, we create controlled moving bottlenecks at some positions, moving at some predefined speed, and use them to restrict the inflow into the congestion downstream of them. So each of the moving bottlenecks that we create is only looking at congestion downstream of it. So the first one will be looking at the lane drop, then the second one will be looking at the congestion left in the wake of the first controlled moving bottleneck, and then so on. So we have them dissipate this congestion by first having them take 2 lanes, which only leaves 1 lane worth of traffic to overtake them. And then, once we calculate that we have restricted the traffic flow enough and that there would be no congestion downstream of them, then we reduce the severity of these bottlenecks to have them only take 1 lane. And by doing that, we are allowing 2 lanes worth of traffic to overtake. And then finally, if there are additional traffic breakdowns happening in the course of dissipating congestion, we simply keep creating new controlled moving bottlenecks until all congestion is dissipated and the road returns to free flow. Now let's have a look at some simulation results. So on the left you see the no control case, and indeed after some time some heavier traffic reaches the bottleneck and we have a traffic breakdown and congestion starts building up. However, with control, as soon as the traffic breakdown happens, we start restricting the flow by creating these 5 moving bottlenecks, and by doing so we are able to keep the lane drop bottleneck in free flow, and consequently we do not suffer from capacity drop. And after some time and after creating some more moving bottlenecks, we are able to return to the unperturbed state of traffic completely. Now, another thing that we can look at is the traffic flow at the bottleneck. So here we have a comparison of the demand with the traffic flows in both of these cases. So you can see in the beginning, while the demand is relatively low, in both cases we're tracking the demand with the traffic flow. However, once this demand rises, then we get a traffic breakdown in both cases. Now, in case we have no control, we're not able to get out of this congestion, so the traffic flow remains at the lower capacity dropped capacity. contrast that with the case when we do have control, you can see that after some time we're able to re-establish free flow at the bottleneck until we have dissipated all of the congestion and finally are able to go back to tracking demand. So all that is left for me to do is to conclude. The point of this work was to find a simple traffic model which is suitable for control design that still captures all of the relevant phenomena that we needed to capture. And our solution to that is front tracking transition system traffic model. So as we have seen, it is fairly easy to model both static and moving bottlenecks in this framework, and we can also handle stochastic traffic breakdown and capacity drop. And furthermore, it is fairly straightforward to extend this model to capture different effects or serve different applications, simply by redefining some transitions or using helper transitions and so on. And we have shown the effectiveness of this model on an example of decongesting a static bottleneck, which is achieved using controlled moving bottlenecks. Some potential avenues for further extending this work might be, first, to explicitly consider the stochastic nature of the traffic breakdown. So here we were fairly reactionary when it comes to traffic control design, in the sense that we only acted once the traffic breakdown has already happened. One might think of a more proactive control strategy where we prevent the traffic breakdown from happening. And then, for example, it would be interesting to extend this model to capture other phenomena such as stop-and-go waves, and also to include observation and use the reconstructed traffic state instead of the perfect traffic state that we assume that we have available to us while doing control design. And we are actually working on this currently. So with that, I would like to thank you for your attention, and I would love to answer any questions that you might have.